Here on problem 32 we have a very long multi-step here, one of the longer ones in the test, which presents a bit of a challenge. The number 15 will be a little bit more challenging. You'll see a little more reasoning goes into this. But here with multi-step, there's no reason to get scared with all the steps. Here, if we carefully draw out each intermediate, you've got to make sure you use your white sheet of paper to draw each of these intermediates that result from that. So let me start that. Here, if we have a reaction with the benzene, they don't all start out with just pure benzene, but a lot of them do. Here we're carrying out a Friedel-Crafts acylation. And here you may have a little difficulty. This oxygen being written right by just carbon like this means we have a CO bond right there, a double bond. I'll draw like that, just so you can see it better. That's what that represents. We've got our catalyst there, the aluminum chloride, and that is going to put that onto the benzene ring. I'll convert that to skeletal now. Notice that the nitric acid here will put the NO2 group on there. In this particular one, you can see what reagents being added, but we could not alternate these here. We can't flip-flop because Friedel-Crafts cannot be carried out after a nitrogen has been put on the ring. So that would be wrong. Just another little exception to remember. So in a way, these syntheses are showing you how to do it, how to do this problem. But yeah, so the nitric acid adds a nitro group, and at this point now we have directing effects that take place. Let's look over here. This is an electron withdrawing group. It withdraws electrons through resonance. Here this is resonance outside the ring because we have this more electronegative oxygen right there. So that's going to take the electrons from the ring out of the ring, and it's going to deactivate that ring right there. So deactivated rings will mainly react in the meta positions. Now if you're having trouble still with this ortho-meta para here, you can just count the meta position here. M is carbon number 3 from the ipso position here, number 1. Ortho is number 2, para is number 4. This is just a reminder. Okay, so it's going to react in the meta position there. Now we have carried out 2 steps. We have 2 groups on the ring, and then we see here this zinc mercury amalgam is added here. That is going to magically remove, just like the last problem, that oxygen right there. Okay. And we get that. Now we didn't have to go through all that process to put that on there, but that's one route of doing it. And the next step now will be to add the chlorine. Chlorine here gets added with the catalyst iron chloride. And since we have 2 groups here, what you want to do is, of these 2 groups, you look for the strongest activator. This one. R groups are stronger activators on the tables there that I gave you. And you can see this is an electron donating group, this is an electron withdrawing. Electron donating groups are activators. So that one there will direct to ortho positions right here and right here. At this point, we don't know which one is going to be selected. We know that this position right here leads to a lot of steric hindrance, and this one is a little less sterically hindered, so is this one over here that is pair to that one. Again, we can label. Pairs are hard to find sometimes when you're drawing. There's the pair position right there. I'm going to go ahead and say that the pair is the most likely pair to what we're going over. So I'm going to go ahead and draw that one and see if we can come up with an answer. If not, we'll go back to the drawing board and we can look at these other two also. I'm just going to do this one just one at a time here though, just to save time. So that is where we substitute. Now you see this last reagent here. This is where I said it would get confusing today. These are all, this is an electrophilic, this is electrophilic, this is electrophilic, and then suddenly we have this thing. What that is a base. If I draw that out there without the sodium, this is just a counter ion. It's got a negative charge, and the negative charge means we have a nucleophilic. That is a good nucleophile. We have a nucleophilic reaction. So let's identify then what kind of nucleophilic reaction mechanism we have. There's two choices. One, we can attack the ring with the nucleophile. Let me go ahead and draw it. And then two, we can form the benzene. Benzene could come out. Smoke a cigar. So to determine that, we look for the electron withdrawing group. If we have an electron withdrawing group already on the ring, then it can react via the addition reaction first. And benzene stays hidden. That's because that nitro group is in ortho position, which is better able to stabilize the negative charge that forms there. Let me do, let me do this partial mechanism here. Okay, there is the NH2 that just added to that carbon. And these bonds are still intact right here. So now this nitro group is stabilizing that negative charge. But the next step is to do that. Reform the benzene ring, and we have an NH2 that has substituted for the chlorine. Alrighty, almost done. So I believe you'll see, if we look carefully at the answer choices here, let's look at these here and compare what we have. A little bit hard to show everything here, but we've got an NH2 right here, which is very similar to NH2 right there. Nitro group, ethyl group, ethyl group. This is the best method here. Have a direct comparison here. Hopefully do it right on your scratch sheet of paper so that you can compare to the answer choices. Not a good idea, unless you're very confident, but not a good idea to go through and look at this thing here and try to match them up. Let's see, this and this, no, you're going to get tricked. All of these are very tricky. So B is the answer on that. Let me go through really quickly, figure out why these are wrong, just as important as figuring out the right one. Excuse me, again, I'm sick. Here, the Cl is still on the benzene ring. If this nucleophilic reaction occurs, that should be gone. That's wrong. Again, another Cl over here. That's wrong. And of course, we didn't carry out a reaction on that one, and somehow that is in the meta position. Not sure how that happened. And this one, this is the devilish one right here. This is a play on eyesight. Right here. The nitrogens are in the wrong spot. Here's NO2 down here, and there's NH2 up there. Somehow these got flipped around from the actual answer. That is a common ploy there that test writers will do.